Okay, now that we've seen in an informal setting the rules for conditional elimination and introduction and biconditional elimination and introduction, let's see how they work in our formal deductive system. So since we're looking at the formal rules, let's do this schematically. All the rules tend to come in pairs, which is an intro rule and an elimination rule. And conditionals are no different. To introduce a conditional, what we do is we assume the antecedent in a subproof, and at some point we prove the consequent that we want, and this entitles us to deduce that if P, then Q. So we have an assumption that P, as we saw informally in the earlier video, and that leads to a further sentence Q, and that's where we derive our conditional by conditional introduction. The elim rule is the rule of modus ponens, which we saw earlier, which is that if we have if P then Q at some point higher up on our line, and later we derive P, then we're entitled to derive Q lower down on the line by conditional elimination. Let's see an example of how this works, which is based on the movie example from the last video. Here's how we construct our conditional proof. First, we assume P with the ultimate goal of showing that under the assumption that P, S holds. Let's number these. By our first premise here, if P holds, then Q or R holds. So on the assumption that P, we're entitled to infer Q or R by conditional elimination. That is to say, modus ponens. Now, we want to show S, so because we have Q or R, we have to do a proof by cases. So we assume Q, and this gives us Q1 and S by another application of conditional elimination. And from this, we can infer S by conjunction elimination or simplification. And then we do the same with the other side of our disjunction here with R. So we assume R, and that gives us R1 and S, which just gives us S. I'll write our rules here. So this is a big proof by cases right here, and it entitles us to infer S from Q or R here. But then our bigger proof is a conditional proof, as you can see here, and this just entitles us to infer S down here on the assumption that P, which gives us if P then S by conditional introduction on 4 through 12. And that's just what we were trying to prove. So you can see that we have a bunch of assumptions going on here, starting off with our main assumption, just P, for our conditional proof, and then our assumption of Q and our assumption of R in order to prove by cases that S holds and thereby conduct a disjunction elimination down here. So this is this blue bracketed set of subproofs, and the whole thing is a set of sub-subproofs for this larger subproof on the assumption that P starting off right here, which gets us the conclusion we wanted down here. So that's how this looks formally, and that's how we would use these rules citing the lines. Now, moving on to the rules for biconditionals, we can see that they come in a pair as well. We have an introduction rule and an elimination rule. The introduction rule, as we saw, is basically a conjunction introduction combined with conditional introduction. If we want to show that P if and only if Q, we assume P and show that Q, and then we assume Q and show that P, and this entitles us to derive P if and only if Q, which is equivalent with Q if and only if P, which is further equivalent with if Q then P and if P then Q. So really this biconditional introduction rule down here is something like a series of conditional proofs where you prove Q from P and P from the assumption that Q, and then you string them together as a conjunction. And I think that's the most natural way to think about it. As for the elimination rule, it's easy to see that if we have P if and only if Q, or for that matter Q if and only if P, then if at some point we get P, we can derive Q. Or if we get Q, we can derive P by biconditional elimination. If you're still a little bit puzzled about this, it is helpful just to think about what the truth table for P if and only if Q is, where assuming that P is true, then Q will be true, and assuming that Q is true, then P will be true in any case in which P if and only if Q holds. And if we've proved it, or if it's one of our assumptions, or it's one of our premises, and in any case it's higher up on our line, then we're entitled to assume that it's true. Let's see an example of a proof which makes use of biconditional introduction, which I think is a little bit more puzzling than the elimination rule. Let's prove P if and only if not P, which will be a theorem of classical logic. Because it's a theorem, we don't need any premises. We can have empty premises up here, and we can just start with the assumption that P. Now let's assume not P for the sake of showing not P. I'm going to number these. Well, here we have a straightforward contradiction, so we're entitled to use our fulsome introduction rule on 1 and 2. That gives us not P down here. So you can see that if we were trying to construct a conditional proof, we'd be done. This just gets us if P, then not P. But we want to run it in the other direction as well. So let's assume, for the sake of deriving another fulsome, not P in order to show that P. We can assume not P and straightforwardly derive a fulsome again, which gets us not P, from which we can derive P by negational elimination on 8. We didn't have to do this assumption of not P in order to derive the fulsome. We could have just taken not P and applied our negational elimination rule down here to get P, and that would have been sufficient. But I thought it was worth going into the detail on it, just to make clear what kind of symmetry exists. And this gets us not P implies P. And now it's just a matter of putting the two together. So notice that we are entitled to derive from this the conditional sentences we have listed here, in which case we could string these together with a conjunction by mere conjunction intro. Or we can just use our shorthand for if P then not P, and if not P then P, which is P if and only if not P. And that's by biconditional introduction on lines 1 through 4 and 5 through 9. And that's how we introduce a biconditional.